Hi, this is Jimmy Chu, and I would like to introduce to you a number guessing game as my capstone project for the PSE core program 2024. This game is deployed in the optimism-testnet, and so you can also try it out at this website. And this project will showcase some basic circuit writing and then building full dApps from end to end, and then it works with the smart contract verifier. Uh, so this includes writing the smart contracts to store the application states, writing a zk-snark circuits that generate a proof on the client side, that is the internet browser, the front end, and then it will submit it on chain and be verified. And the whole state will be stayed safe in the smart contracts. So the purpose of the game is actually for each player to guess closest to the means of all the submissions by all the participating players. So we can come to this website, and I have I'm already connecting to the Optimism testnet here. You can see in the MetaMask, this is Optimism Sepolia. And I have three different users with different address connecting to it. So first, I will walk through creating a new game and walk through the whole game together. Feel free to speed up the video so you don't have like you can shorten the time on the transaction processing. So I'll create a new game. MetaMask is shown, and a new game has been created. And for the other users, if they refresh the screen, they will see a new game here. They can join the game. Right now, there's only one player who is the game host joined the game. So this second player will join the game, and the third will join as well. Now, after joining the game, you see that on the second player window, there's two players already joined it already, and then this one, you'll see that actually if you refresh, you'll see that this one hasn't joined yet. Okay, let's join again. All right, you'll see three players. This one is the 1-9, blah blah blah. Three players joined the game. Now we can start the game. The one from the blue windows is the game host. He can manage the flow of the game. So we'll start the game. Now everyone can submit a number. All right, three players. And then now this the number will be from 1 to 100, between 1 to 100. So we will submit, say, 50. So when we click this button, actually it goes through zk-snark circuits and then generating a public signal and proof. And we are just submitting the public signals and the proof on chain. So it actually take a little bit more amount of the transaction fee, of the gas fee here. So confirm. So you see that actually the committed value is 50, and then a nullifier has been randomly generated. And you'll see from the UI that one player has submitted the commitment, and this is round one. Oh, and actually the players that win 3 rounds, the first player that wins 3 rounds will win the game. So this player has submitted a commitment, and then the second player will do. So this one will submit a 20. And this will submit an 80. So these values are not stored on chains, but actually their hash are stored on chains. So what is stored on chains are the Poseidon hash of the nullifier and the Poseidon hash of the value and nullifier together. All right. Now the commitment has been submitted. Now they can open it. So when we inspect the on-chain storage, people won't know what values are actually stored on-chain, what the actual value, because they are only storing the hash. And now we can open. If we refresh, this is a point of like we can room for improvement on the UI that it can subscribe to the chain on-chain event and then refresh the screen automatically instead of like doing a refresh manually like here. And now we can open the commitments. Actually, the previously submitted values and the nullifiers are stored in local storage, so you don't have to uh, like we don't prompt you again. The UI don't prompt you again. But if you want, you can activate the advanced mode and change the commitment uh, later, and change the commitment and then submit again. We can try that later, but let's open one round of commitment first. So when you open the commitments, you are basically submitting the previous submitted values together with the proof, but with the input signal public. So we open the commitment. Now the second one will open the commitment as well. This is a 20. This is I believe the blue the player with this blue frame should win, right? All right. Now let's try if we mess with our commitments. Previously we submitted 50, right? This is a loading from the local storage, and this is the nullifier we generated. Let's see if what happens if we mess with our commitments. So we say that we actually say we uh, uh, said we previously submitted a 5 instead of a 50. To see what's happened, we have to open the dev console. And now if I open the commitment, you would actually see an error message here saying the contract function execution error. And the error is coming from a guessing game unmatched commitment. So actually the on-chain verifier will verify that this is not the previous commitment that we have made. So we have to actually open it, we have to submit the same commitment value that we sent previously. So we previously sent a 50, so now we open it again. All right, we have committed or open the commitment. So all the players have opened their commitments, and we can conclude a round. There's one pending transaction. We can conclude the round. And then the winners will be determined. I believe, yes, the blue screen, the player with the blue frame wins. So you see a medals, and you also see the round one winners is this guy, and his winning submission is 50. So the actual means are not shown, but only the winner submission is revealed. I think this will make the game more interesting because you don't actually know the actual means, but so the players will try to guess based on the information they see, like the submission of 50 wins. So what will be their next bid or their next submission value? So we will go through the second and third rounds quickly and finally end the game here. But basically you get a flow of what this uh, number guessing game is about. So I'll do all right. I'll do 80. And this one will, okay, all right. So need to refresh the screen, need to refresh. This will do 79 because just now I did 80, 79. And this will do 81. All right, so this player will win again. So now each player can open their commitment. We refresh the screen. Okay. We don't need to test this again, advanced mode, but basically you can try mess with your own commitments and submit it and see what happens. So the players take turn to open their commitments. All right, so we can conclude round 2. We can conclude round 2, and we this blue frame player win again. The blue window player win again. And oh, just if you go back to the homepage, you can see that the game has been in progress. Well, it's hidden by the footer, but it's in progress, and it has been to the round 3. There are 3 players. There can be more than 3 players. You can try it out, right? And we'll make this say 50. $50, $30. And let's do an 80 here or 70 here. Now 3 players have submitted their commitment. Now they can open it. And this will conclude round 3. And this blue window player should win again and end the game. 50 is opened. $70. Oh, then the yellow window player may win, isn't it? Oh, okay. Yeah, the blue player, the blue window player. All right, we can conclude round 3. And the game ends. The first player wins 3 rounds, and this blue window player will have won 3 rounds. So the winner of this game is this guy. And the game has ended. All right. And we can actually okay. So the project is actually is in here. PSE core self capstone, and we will go through about the origin of this project. Actually, it's coming from the semaphore template, and I've learned a lot from reading the semaphore source code and semaphore boilerplates. But let's get to that later. All right. Let's inspect the smart contract. The smart contract is deployed on optimism-testnet, so we can see it here, the optimism Sepolia. Let's take a look at the guessing game contracts. I just want to show on-chain what is being stored on-chain. So the contract has been verified, so we can read the contracts. Just now we are on the second game. So the game ID is 1. So if we look at the game ID, right, what is being stored is actually get player commitment. Yeah, what is being stored at the submission commitment phase is actually at the player commitments. So if we say game ID 1, say round 10, and then the player address, this one. You would see that this is actually a two big number. One is this, the second one is this, and this is actually a Poseidon hash of a nullifier and value with a nullifier. So it is actually shown in the circuit source and submission checks. Whoa. All right. So actually, this is the two values, submission and nullifiers, the Poseidon hash being stored on chains. And when you look at the opening, you will get back the actual values, 50. Yeah. All right. So this is basic zk-snark dApps. It has 3 components. Again, the circuits, the smart. The circuit is actually simple. You see, like it perform a range check saying that it has to be between min and max, which is defined here, from 1 to hundreds, min and max, and then n bit is a number of bits used for checking. So 7 bits will contain all 100 digits, and then generating these 2 outputs, right? One interesting thing is that the submission commitment verifier and the opening commitment verifiers are actually the same code, basically. Yes. It is all using the submission check templates, but just that in the commitments, you see that there's no public inputs, but in the open, there's a public inputs in and rands. So you put that the inputs and the nullifiers, and this is the nullifiers, as public inputs, so that it will refill the input as well in the proof generators. Okay, so this is circuits. This is a game contracts. The guessing games pretty much store all the game states here. All the applications logic are stored in these contracts. So this acts like a backend of the games, and these 2 are the verifier contracts. This is a commit verifiers. This is an open commitment opening verifiers. All right, and then the third component is the web. The web contains the front end of the website. And all right, and the smart contracts has been can be inspected here. Deployed contract address can be inspected here. All right. So finally, I need to attribute these projects to the Semaphore team, because I basically this again you can see that these projects is generated from this Semaphore templates. I've modified a bit, but basically the whole structure and the way it architect the projects and how they use SOCOM kits, basically some SOCOM kits to simplify the circuit development workflows. So that is very nice. And then how they structure the UI there. So I've learned a lot. And again, thank you for the opportunities of allowing me to join the PSE core programs. I've met good friends, and and learned it a lot. I've read different papers from Grok 16 to PLONK, learning about the zero knowledge snark, zero knowledge proof, things about zero knowledge proofs, and finally I'm able to put that all of this like knowledge into into practice, and then build this dApp from end to end with all different components and connect them together and deploy it on a testnet. So I'm quite happy about this, and hope uh, like I hope this project could be something that would be useful, or maybe something that you can get some inspiration from. And this is definitely just the beginning of my learning journey in zero knowledge proof, and I look forward to do more with zero knowledge, and hope one day I could make more videos and then to demonstrate more cool project later. Thank you.